In this video, we're going to look at the concept of cell potential in electrochemistry, look at how you can use it to know when a reaction is spontaneous or not. We also look at the relationship between cell potential and Gibbs free energy, and also the relationship between cell potential and equilibrium constant K. Alright, so let's begin with this. Now, in electrochemistry, cell potential is calculated using, so this is how you denote cell potential. This is standard cell potential equals the oxidation half potential plus reduction half potential. Alright, now note that when the cell potential is positive, the reaction is said to be spontaneous, whereas when cell potential is negative, the reaction is said to be not spontaneous. Alright, so take note of this difference when it's positive and when it's negative. Okay, so having known this, let's wipe this now and look at a typical question or problem on this and solve it together so that you understand it better. Okay, so let's look at this problem. It says construct a galvanic cell using the 2-half cell reaction and predict whether the reaction is spontaneous. Okay, so we have the 2-half cells to be this. This is 10. Okay, lost 2 electron here to form 10 atom. This one zinc lost 2 electron to form zinc atom. So we have their respective standard electric potential to be these values. Alright, so they're measured in volts. Now note that 2-half cell and their potential will always be given in their reduction form. Alright, so we have to reverse one so it can act as the anode. Usually the one with the smallest electric potential will serve as the anode. Alright, now in this question, the least electric potential here is minus 0.763 volts, which shows us that this half reaction zinc will serve as the oxidation half reaction. Alright, okay, before we do it, remember we have to reverse it before using it as the oxidation half reaction. So if we reverse it, it's going to be zinc will be composed to give zinc ion losing 2 electron, as well the electrode potential the sign will change, now be plus 0.763 volts. Alright, now we can calculate the cell potential. Remember, the cell potential is oxidation half potential plus reduction half potential, and this is now our oxidation half reaction. Alright, so if we want to write the overall reaction for the overall reaction will be, so we're going to have it to be 10 alright ion plus zinc atom will yield zinc will yield 10 atom rather, right, plus zinc ion. So this will be the overall reaction for it. Okay, so let's go ahead and find the cell potential. Standard cell potential will be, so the oxidation half potential is now plus the 0.763 plus, right, this one we have the reduction half potential to be minus, within brackets, minus 0.136. So plus times minus something as 0.763, alright, minus 0.136. So let me punch it in my calculator. Okay, so I have it to be 0.627 volts. So this is the positive cell potential. It shows that this reaction is spontaneous since it's positive. Alright, let's wipe this now and solve another problem. Okay, so let's look at this problem. It says predict whether a galvanic cell can be constructed with the following two half cells. Alright, so we have the two half cells. So as usual, the half cell with the least electric potential will serve as the oxidation half cell, since they are usually in reduction form, the two half cells you're given. So the least electric potential here is minus 1.66 volts. So we're going to reverse this half cell. So if we reverse, we're going to give us aluminium. We decompose to give aluminium ion plus 3 electrons, losing 2 electrons. Alright, so the electric potential will not be the sign will change plus 1.66 volts. Okay, now if you look at these half cells, you will notice that their charges are not equal. The electron gain is not equal to electron loss. Like here we have 2 electrons, we have 3 electrons here. So to balance the charges to ensure that electron gain equal electron loss, for this reduction half cell we have to multiply everything here, make it a coefficient, multiply everything here by 3, and multiply everything here by 2. So let's begin with the reduction half cell. If you multiply by 2, we're going to have 3 sulfate ion, right, plus 3 times 4, 12, right, hydrogen ion, plus 3 times 2, that's 6 electron, plus, right, we yield 3 sulfurous acid, right, plus 3 water. Where the oxidation half cell, if you multiply by 2, you're going to have 2 aluminium to yield, right, 2 aluminium ion plus 2 times 3, 6 electron. Alright, so you can see now the electrons are now balanced, 6 and 6. Note that this multiplication will not affect the electric potential, the values here and here. Alright, so we can now go ahead and find the cell potential. So that's oxidation half potential plus reduction half potential. So when you put the values, I'm going to have it to be 1.66, right, plus 0.17. So let me punch it to my calculator. Okay, so I have it to be 1.83 volts. So this reaction is spontaneous because it's positive, the cell potential is positive. Alright, so having known how to do basic calculation with cell potential, how to find it, now let's look at the relationship between cell potential and Gibbs free energy. Let's wipe this. Okay, so the relationship between cell potential and Gibbs free energy is given or is expressed like this. Alright, we have it to be changed and standard Gibbs free energy equals minus N, which is the number of moles of electrons involved in the redox reaction, times this constant times cell potential, standard cell potential. Alright, so this is the relationship between Gibbs free energy and cell potential. Alright, so having known this, let's wipe it now. Look at the typical problem on this. Let's solve a question on this. Remember the file this constant is 96,500 coulombs. Alright, so let's wipe this. Okay, so let's look at this question. It says electrochemical cell reaction in a cell made up of the following half cells. So these are the half cells with their respective standard electric potential. It says what is the free energy change for the half cell reaction. Alright, so we're going to apply this formula. Change the standard Gibbs free energy equals minus number of moles of electron involved in the redox reaction times this constant times cell potential. Alright, so let's begin with find the set potential. The set potential, as we all know, set potential will be oxidation half potential plus reduction half potential, right? So in these half reactions, we have the electric potential with the least value will serve as the oxidation half reaction. Okay, so this half reaction that has this electric potential to be 0.17 is a least, so it's going to serve as oxidation half reaction. So we have to reverse it before we make use of it. So if we reverse it, we're going to have it to be, so we have sulfurous acid, alright, plus water, alright, we yield sulfate ion plus 4 hydrogen ion plus 2 electrons, so lost 2 electrons. Now if you check, the charges are not equal, the electron loss is not equal to the electron gain. Here we have 5, here we having 2, so to balance the electron we need to multiply this reaction here, which is the reduction half reaction. We multiply everything here by 2, then multiply everything here in this oxidation half reaction by 5. Right, so when you do it, you're going to have the new half reactions to be, when you multiply the reduction half reaction by 2, you're going to have it to be 2. Alright, we have manganate 7 ion. Okay, manganate 7 ion plus 2 times, so we wipe this, 2 times 8 for hydrogen, we need to have it to be 16 hydrogen ion, then plus 2 times 5 electron here give us 10 electron. Alright, we yield 2 manganese ion, alright, then plus 2 times the 4 here give us 8 water. Right, note again that it does not affect the electric potential, it still remains the same, 1.51 volts. Alright, since we reverse this one, the electric potential will now be minus 0.17 volts. So when you multiply the oxidation half reaction by 5, you're going to have it to be, okay, 5 sulfurous acid, right, plus 5 water, we yield, okay, we have 5 sulfate ion, right, plus 5 times 4 will give us 20 hydrogen ion, plus 5 times 2 electron will give us 10 electron. So the electric potential is minus 0.17 volts. So as you can see now, the electron here is not the same with the electron here. Alright, so very important, this is 10. Alright, so now that we have done this, let me wipe it up so that we have space to complete this solution. Okay, we cannot find the set potential, so it will not be the oxidation half potential, which is minus 0.17, alright, plus reduction half potential, which is 1.51. so let me punch it in my calculator. Okay, so I have it to be 1.34 volts. Right, so this is the set potential. Remember, we're going to apply change in standard gauge free energy equals minus NF set potential. Right, so in this question we have gotten our set potential to be this value, and our N will be, which is the number of electrons involved in the redox reaction. So number of electrons have it to be 10, so they are equal, have it to be 10 electron, and Faraday's constant is 96,500 coulombs. So when you impute it in this formula, the change in Gibbs free energy will be minus 10 times Faraday's constant 96,500 coulomb, right, and the cell potential is 1.34. So let me punch everything in my calculator here. Okay, so I have it to be minus 1,293,100 joules, right? If you want to leave it in kilojoule, divide it by 1000. If you divide it, it's going to give you minus 1,293.1 kilojoule. Alright, so this will be the Gibbs free energy for this reaction. Okay, let's wipe this now and look at the relationship between cell potential and equilibrium constant before we call it a class. Okay, so let's look at this question. So calculate the equilibrium constant for the reaction between the two half cells at 25 degrees Celsius. So we have the two half cells with this. So now note that the relationship between cell potential and equilibrium constant is expressed as, so we have cell potential equals ideal gas constant times temperature, alright, ln K all over number of moles of electrons involved in the redox reaction times Faraday's constant. Alright, so this is the relationship between cell potential and equilibrium constant K. Alright, so for this problem, to solve it, we need to get the cell potential, and we know that cell potential equals oxidation half reaction plus reduction half reaction. Alright, so in this problem, the electrode potential with the least value will serve as the oxidation half cell. Alright, okay, so the least electrode potential cell value here is this zinc reaction. This one here is 6, so which is minus 0.763 volts. So we're going to reverse this reaction and use it as the oxidation half reaction. So if we do it, it's going to give us zinc decomposed to give zinc ion plus 2 electrons. So the electrode potential value will change to plus 0.763 volts. Alright, so now we can find the cell potential. Let's plug in the values. They're going to give us, so we have 0.763, alright, plus, in bracket because of minus 0.136. So this is the same thing as 0.763 plus minus minus 0.136. Now let me punch it in my calculator. Okay, so it's going to give 0.627 volts. Alright, so now that we have gotten the cell potential to be this value, now the N, our N will be the number of electrons involved in the redox reaction. So we have the number of electrons will be 2, since the electrons here are equal. No need multiplying anything, any half cell by anything to balance, since it's already balanced. So the N number of moles will be 2, right? And our Faraday's constant F is 96,500 coulomb. Alright, so our ideal gas constant R is 8.314 if we are leaving it in 2 decimal places, and our temperature in this question is 25 degrees Celsius. So convert it to Kelvin, that's 25 plus 273, which will give us 2 298 Kelvin. Alright, so now we have the parameters. Let's plug them in this formula we have here. So when you put it, you're going to have, let me wipe the up. Okay, so you're going to have the C potential is 0.627 equals, and the gas constant is 8.314. Alright, then times temperature is 298. Right, so this is 2, then times length K over the mole, number of moles, 2 times this, sorry, for this constant is 96,500 coulombs. So when you cross multiply, you're going to have 2 times 96,500 times 0.627. Let me punch it to my calculator. Okay, so you're going to have 121,011 equals, let me punch 8.314 times 298 with my calculator. Okay, so it's going to give 2,477.572 lane K. Okay, so you divide both sides by this value, 2,477.572, right? 2,477.572. This will cancel this, right? So our lane K to be 7 divide what we have here, 121,011 divide that value below. Okay, so it's going to give us 48.84257. Alright, let's leave it in 5 decimal places. Now to get the value of K, you divide both sides by lane. So our K will now be the lane inverse of this value, 48.84257. So when you punch it with your calculator, you're going to have lane inverse give you exponential to the power 48.84257. So let me punch it with my calculator. Okay, so you're going to have it to be 1.63 if you're leaving it in 2 decimal places here, right, times 10 to the power 21. So the equilibrium constant does not have a unit, so this will be the value of K, 1.63 times 10 to the power 21. And with this, we have come to the end of the class. So guys, this is basically how you can solve problems involving set potential, relationship between Gibbs free energy and set potential, and relationship between set potential and equilibrium constant K. Hope you learned something interesting. If you are new to the channel, you should hit the subscribe button to subscribe for more videos. So like, share, and comment in the video. Tell me how you feel about what you have learned. If you seem to have any specific questions to ask, feel free to leave a question in the comment section below, and I will sure to give you a response. That's it for this class, guys. Thanks for watching.